Welcome back to Monkeys on Typewriters on YouTube. And in this episode, we're looking at part four of the discussion around evolutionary biology and cancer. And you may recall from last episode, we started hearing about SARS-CoV-2 and its potential role as a carcinogen. And we're going to follow up in this episode with a discussion of how you might go about proving that and how challenging it may be to do so. So, Arijit, I'm happy to hand it over to you, and let's see part four.
Great. Thanks, Ryan. So we're going to do a quick recap of what we covered in the previous three episodes, just to make sure that we refresh everyone's memory. If you weren't binge watching them, you might appreciate it. But anyway, so let's jump right in. So we've talked about the evolutionary paradigm of cancer. So there's a traditional belief that cancers are driven by oncogenes, and that belief has kind of gotten really nibbled around the edges, and I would say it's almost sort of a dying belief at this point. Not that oncogenes don't exist, but the notion that oncogenes drive cancer has really kind of bumped up against some heavy going when it comes to aligning with the data. You can knock oncogenes out, as I have in my time in pharma, and I've been responsible for cell biology groups and biochemistry teams and in vivo pharmacology groups where we knocked out the oncogene in question with a small molecule drug, and lo and behold, the tumor was just fine. So the oncogene paradigm, as we covered in earlier episodes, has had sort of a competitor for a number of years, and that is the evolutionary paradigm of cancer, which is basically that cancer is not many different diseases, it's one disease. I didn't say that wrong. It's not many different diseases, it's one disease. So what it is, it's a process of somatic dominant evolution. It starts out with chromosomal instability, which basically is a process by which cells start dividing inappropriately and gaining and losing individual chromosomes with each division. So what that does is it creates a stochastic accumulation of mutations. And then each patient has a unique natural history in the same way as you can think of a natural history tree or tree of life. And in this particular case, an individual patient's cancer could have many different tumor genotypes. So when people have section tumors, for example, post-mortem, they found that different parts of the same tumor will have very different genotypes, and the primary tumor and the Mets will have very different genotypes usually. So this is kind of what it looks like, and it doesn't necessarily fit the oncogene model plainly. And so you could say, well, that sounds nice, but isn't it just semantics? And the answer is no, it's not semantics, because when we studied the oncogene paradigm in high school or in college, what we learned was that the oncogene was the accelerator and the tumor suppressor was the brakes. This is how we thought of cancer, right? Well, given that no particular gene in our body exists for the sole purpose of giving us cancer, obviously this model didn't pan out. The chromosomal instability model is a bit different. It's like releasing the handbrakes in a car that's parked on a hill. When chromosomal instability is initiated, and it's usually initiated by a set of events that often has to do with unrepaired DNA double-strand breaks. DNA double-strand breaks, when they form inside a cell, the cell halts where it is. It goes into a checkpoint in either G1 or G2. But in some cells, when those checkpoints are defective, usually due to actually tumor suppressor mutations, then cells barrel right through that checkpoint in the presence of DNA double-strand breaks. Now, DNA double-strand breaks during division are really bad news, because when cells try to line up their chromosomes, if you remember in mitosis, where all the cells line up neatly in one place, when cells try to line up their chromosomes in mitosis and they have DNA double-strand breaks, then the forces become imbalanced and weird stuff starts happening. So chromosomes get missegregated. One cell may have 23 pairs, 23 plus one, and the other cell may have 23 minus one, so to speak. So where you end up is essentially a gain or a loss of a chromosome in every division. And what that does is it creates a process of essentially somatic mutation accumulation very quickly. So once the handbrake is released, the car rolls down the hill. You can put the handbrake back on, but it won't help. That's what happens. Once that process is initiated, you can go ahead and inhibit the oncogene. It's not going to help you, which is what we found for many programs that I was actually the discovery project lead for. We would inhibit the oncogene and nothing would happen in some tumors, and there are other tumors that would work. That's not what oncogene addiction says. But the chromosomal instability paradigm, most importantly, is hit and run. So in other words, once the oncogene has done its thing, It doesn't need to be present. Importantly, the chromosomal instability paradigm, if you look carefully, doesn't need an oncogene. What it needs is double-stranded breaks. So in fact, when we try to apply this now, we ask the question, well, how does this map to what we know about viruses and cancer? It turns out that oncogenic viruses all generate the same cellular insults. They generate DNA double-strand breaks. They then have DNA damage responses that are usually defective, as we discussed, and they have gain and loss of chromosomes, which is called chromosomal instability. But you also see a couple of other things when chromosomes are lost and gained, such as micronucleus formations, that tiny nuclei that form inside a eukaryotic cell where they're not supposed to be, which are essentially one extra chromosome that was lagging, couldn't figure its way out. And when the time came for the division to end, just ends up in its own little nucleus off to one side. Its own micronucleus. Micronuclei are both contributors to, they're both causal and characteristic of chromosomal instability. So the 7 viruses that are known to cause cancer all show these defects. So you have double-strand breaks, DNA damage response, you have micronuclei and chromosomal instability. We talked about this last time, but as it so happens, SARS-CoV-2 generates the same cellular insults. So if you add that to this panel, what you get is SARS-CoV-2 cleans up. So it also causes DNA double-strand breaks. We saw last time several different papers that showed it 6 ways till Sunday. DNA double-strand breaks with what's called Western blotting, looking at the actual presence of DNA double-strand breaks, a protein that binds to DNA double-strand breaks called gamma HJX. We saw that same protein in immunofluorescence microscopy. We also saw COMET assays, which are where they take nuclei and migrate them through an agarose gel. And we saw the DNA double-strand breaks leading to fragmented DNA in cells that have been infected with SARS-CoV-2. SARS-CoV-2 proteins are known to disrupt the DNA damage response. And again, cells infected with SARS-CoV-2 have been shown by several different groups to show chromosomal instability as well as micronuclei. So it's not up for any kind of serious debate that these insults happen. Not only that, but SARS-CoV-2 also causes a bunch of other insults that on their own are sufficient to promote cancer progression. This is, again, very well documented. This is from a review paper. I modified it slightly, but the paper essentially talked about all of these different pathways. And so it causes cytokine release, it causes tissue hypoxia, causes oxidative stress, and it also causes reactivation of oncogenic viruses. So if nothing else, if it was just that it was reactivating oncogenic viruses, that would make it carcinogenic in and of itself. But the point is, in addition to the direct cellular level, cell autonomous insults we talked about in the previous slide, here are tissue level or non-cell autonomous insults also that are capable of causing or promoting cancer progression. So there's quite a few of them. In our first episode, we talked about, or this was the second episode, we talked about sort of what's a checklist, what's a good checklist for viral carcinogenesis. So it makes sense to say the virus should cause persistent infections and it should infect dividing tissues. And then we talked about the cell autonomous insults like DNA damage and micronucleus formation. Then we also talked about secondary mechanisms such as suppression of signaling of the cGAS-STIM pathway, apoptosis, and so on. So all of these things are present with the first 4 or the first 3 bullets are present in all of the viruses that cause cancer. And many of the viruses that cause cancer also have stuff from this bottom list over here. SARS-CoV-2 cleans up on this list. So we talked about this again last time, and it would be surprising, as we discussed, it would be surprising if SARS-CoV-2 was not carcinogenic. So now, this is the point at which most people will say, well, but what does the data say? What does the data say more specifically, right? And what they mean is, where's that wave of cancer? Are we seeing a lot of people getting cancer or not? And so in the next part of the presentation, I'm going to explain to you why that is a trap and why getting into that conversation about where are all the cancer cases is a futile conversation for all concerned. So the first thing to keep in mind is that most risk factors increase your risk of cancer only very slightly. So these are the top 10, top 9 things that increase your risk of cancer. And of these, alcohol, obesity, radiation, you'll be shocked to see what their risk factors are. Cigarettes are pretty clear-cut. You have a 100-fold higher risk of getting cancer if you smoke cigarettes. 100-fold. Of squamous cell carcinoma, lung cancer 100-fold, adenocarcinoma 20-fold. On the other hand, alcohol, this is what it looks like. So if you drink 2 drinks a day, you have a chance, you've got a 10% increased risk of cancer. So 100-fold is a 10,000% increased risk. And this is 10% increase in risk. Obesity increases your risk of cancer by 70%. When people talk about these things being bad for your health and causing cancer, specifically when they talk about cancer, they're not comparing apples to apples because nobody talks about the hazard ratios. But the hazard ratios matter because those are those are the practical things. You can always get a statistically significant effect. The question is, how big was the hazard ratio? So obesity is a 17% increase. Radiation, um, if you happen to be on the outskirts of Hiroshima on August 6, 1945, your lifetime risk of cancer increase was about 50%. So these are really small numbers for things that we usually think of as being very, very carcinogenic. So except for cigarettes, everything else is a really small increase in risk. So let's keep that in mind because that matters. So in order to prove, for example, that obesity would lead to an increase in cancer risk, it's a long drawn out process. Um, the link between alcohol and cancer, long drawn out process. When you look at cigarettes, cigarettes cause an increase in risk of about 100-fold. This is what it looked like when you looked at lung cancer incidence versus per capita cigarette consumption in the first part of the 20th century. It took about 20 years to have any kind of like appreciable increase, or 30 years almost, to have any kind of increase in lung cancer. People didn't even care about it until about the 1930s. By the 1960s, it was clear that there was a rise in lung cancer risk and it was tracking with cigarettes. So at this point was when cigarette smoking peaked. There was, from the 40s onwards, there was a lot of noise about this, by the way, and we'll talk about that. But when laws got passed in the 60s to make it harder to start smoking, 60s and 70s, it still took another 20 years for lung cancer rates to level out and then start going down. So there are huge delays both on the way up and on the way down. And this is really important, not only on the way up, but also on the way down. It takes a long time to recognize something is carcinogenic from epidemiological data, and it takes a long time to fix the problem. And now this is with epidemiological data of with 100-fold. You can imagine when it's less than that, how much more insignificant that will be, or how much harder that will be to detect. Now, it was actually long known that cigarettes were harmful. By the 1850s, or the 1880s, they were calling them coffin nails. At the turn of the 20th century, there was an anti-smoking movement, more linked to the temperance movement, but that managed to get cigarette sales banned. And when it comes down to it, this is a poster from 100 years ago. This is a Soviet quit smoking poster from 100 years ago. So think about that for a minute, because it wasn't until the 60s or 70s until action really started. And most of us who are Gen X or older remember very well a time when all our buildings smelled of cigarette smoke. It really didn't change until the late 80s. So if you look at it from the 1940s onwards, there were noises being made about carcinogenicity. In the UK, statisticians drew attention to the increase in lung deaths by the late 40s. By the early 50s, there were really clean studies showing large increases in risk of death. And we'll talk about that. Here's one example. This is from the early 50s. And what they showed was they looked at doctors and their smoking habits. And essentially what they showed was that there was a really strong correlation, which makes sense. It's a 100-fold increase in risk. This is what it looked like. Your average number of cigarettes smoked daily and your annual death rate. It was really eye-popping. 1954. So you'd think by 1955, no one was smoking, right? No, it took a really long time. 1964 was when the Surgeon General's report said, well, it may need to be dealt with. And in 1966, 2 years later, it was cautioned cigarette smoking may be hazardous to your health. But all of this took a really long time. There was a huge amount of inertia after. So first, it takes a really long time to detect a cancer risk, even when something's highly carcinogenic. Then it takes a really long time for people to do anything about it. And after it takes a really long time for people to do anything about it, we shall see that it takes a really long time for anything to happen in terms of epidemiological numbers. There was a 30-year gap between when action started on cigarettes and when the rates started falling, which is consistent with the 30-year time lag for the amount of time it takes to develop cancer. So The important thing to remember here is that causality for carcinogenesis is different from how we understand causality on a day-to-day basis. On a day-to-day basis, we say, don't stand on that ledge, you'll fall to your death. And what that means is if you stand on that ledge, there's a good chance you will fall to your death. So there's like a causality, it's pretty clear cut. They stood on the ledge, they fell to their death. So if A causes B, if you do A, it'll result in B. But carcinogenesis is not like that. It's a stochastic process. So it violates our day-to-day understanding of causality. Smoking is neither significant, neither necessary nor sufficient for lung cancer. You can get lung cancer without smoking. You can smoke and not get lung cancer. It happens all the time. Most smokers don't get lung cancer. I think 70% of smokers don't die of lung cancer. And not all lung cancer patients were smokers. Sorry, 85% of smokers don't die of lung cancer if they're male. 90% of smokers don't die of lung cancer if they're female. And carcinogenesis, as I said, is a delayed process. It takes decades. Smoking also causes cancers other than lung cancer. And all of this confusion around causality was weaponized to the fullest extent by what's called the merchants of doubt, the people who were being paid by the tobacco industry to create confusion. They used this playbook and this particular set of facts that you see in this slide to delay action by years. Now, with viruses, what is the scale of carcinogenesis risk? Let's talk about that. So, first of all, viral attributed cancers are common. We know at least 16% of all newly diagnosed cases of cancer are due to viruses, which is really shocking. We didn't even know this 30 years ago. 30 years ago, we thought, well, in theory, viruses should cause cancer, but they don't. All of this stuff has come out in a relatively recent time frame. And as you can see, one interesting thing here that you notice is that hazard ratios are very variable, and it's not necessarily the most common viral infections that lead to the most cases of cancer. So when you look at the hazard ratios for oncogenic viruses, they're all over the place. And what that means is that the burden of cancers is not linked to the burden of the viral diseases. You'll notice though that they kind of span from 1.8 to 75. HPV, if you have persistent HPV, your risk of cervical cancer goes up a lot. But otherwise, it's 1.8 for EBV and 15-fold for HPV-HCV. So you don't really know if COVID is carcinogenic, you don't really know where it will fall. But if it falls somewhere in that spectrum, if it's on the lower end of that spectrum, good luck figuring that out in our lifetimes with epidemiological data. It would be designed, a course of action that argued for inaction until epidemiological data would be designed to do nothing for a generation. Keep in mind also that virus and cancer associations are not always straightforward. It's not like every virus causes cancer in only one tissue. They often cause cancer in more than one tissue. They're not always necessary for a given cancer type, obviously. T-cell leukemia happens without HTLV1 infections. They're not always sufficient for cancer types. So just because you have hepatitis B doesn't mean you're going to get hepatocellular carcinoma. And they're not specific either. So all of this will mess things up. And a virus like COVID, which infects a wide variety of tissues, may end up causing a wide range of different cancers. So this will make it even messier. Keep in mind, as we discussed, that the oncogenic paradigm of cancer does not allow for viruses to not be present when in the tumor. So the way that they established the link between those cancers and those viruses was that the viruses were found in the tumors. Now, that doesn't necessarily have to happen if it's initiated through chromosomal instability. For SARS-CoV-2, the mechanism is almost certainly chromosomal instability, not an oncogene. And SARS-CoV-2 does not integrate in the DNA. So the traditional way, the way in which we found other oncogenic viruses in the past, won't work for SARS-CoV-2 right off the bat. Viral infection induces DNA double-strand breaks. The precancerous lesions may contain evidence or may not. But once the chromosomal instability is present, the virus no longer needs to be around. So there's no need in this formulation of SARS-CoV-2 mediated carcinogenesis, there's no need for the virus to be present in tumors. Keep in mind that the presence of other viruses doesn't always track with cancers anyway. So herpes viruses are present in many different cancers, and viral presence in tumors is neither necessary nor sufficient. All of this is to say that, yes, there are ways to establish viral carcinogenicity, but in general, establishing viral carcinogenicity in the traditional ways relies on very simple kinds of viruses and viruses that hew to a particular kind of mechanism that was very strongly driven by the oncogene hypothesis. Once you come away from the oncogene hypothesis, these kinds of approaches don't work that well. The other thing that people have done in the old days is transformation assays. So does it cause cancer in mice? Well, viral infection is species specific. So when you look at, for example, if you're trying to study HCV, well, in order to study hepatitis C virus, there are many different models, and you have to kind of mix and match the models to learn what you want to learn. And in fact, wild type human HCV does not infect mice. So you have to use mouse adapted HCV, or you have to use humanized mice. The whole thing is messy. The whole thing is kludgy. And it's like this for pretty much every single virus out there. So you can't really use these models, and they were never used to establish that these viruses were carcinogenic. They were used to study these virus-induced cancers once we had established that the viruses were carcinogenic. So here's another, here's three more as examples. So in general, like, again, animal models don't help you that much. So the presence of DNA doesn't help you. Integrated DNA doesn't help you in this case with SARS-CoV-2, obviously. Presence of oncogenes doesn't help you. Animal models don't help you. Then there's the clonal transformation assay, another blast from the past. They used to put viral cultures down, and then with those viral cultures, they would isolate the virus from those cultures. Then what they do is they take monocytes from blood, take whole blood, spin it down, pull out that white layer in between the plasma and the red blood cells. That contains the white blood cells. And those white blood cells cultured with monocytes again lead to, if you can then take those and you culture without a feeder layer, you can transform clones of other cells. So in other words, you amplify the virus that you isolated from culture, and now you throw it back in other cells, and you show that these monocytes, which are not going to grow, like they're not going to be transformed normally, start growing uncontrollably, or start growing essentially like a cancer. Right. So the transformation assay relies on two things. It relies on being able to isolate the virus back and then throwing it into monocytes and seeing what happens. And again, this is a messy process, and it doesn't usually work that well. It worked for EBV. It hasn't worked for other cancers. If you look at the number of hits from PubMed for the transformation assay, again, it's a dated assay. And that's it. From 1990 to 2024, in the last 34 years, HTLV1 has had three papers, count them three. HPV, three papers, and EBV has had a few more in the past 50 years. But it's a really uncommon assay, and for good reason, because it usually doesn't pan out. So it's relying on the oncogene assumption as well. So other viruses such as HCV, HBV, Kaposi sarcoma, Merkel cell polyoma virus, no hits for the transformation assay. So the transformation assay is neither necessary nor sufficient to show that something is carcinogenic. Koch's postulates don't work either. So Koch's postulates are where you isolate the infectious agent from an animal that's suffering the disease, put it into another animal, and show that that's what happens. Show that the same disease is caused. So this is a 19th century thing, and it's great. It's really great for certain kinds of infectious disease, right? But if you modify the Koch's postulates for SARS-CoV-2 induced cancer, then this is what you'd ask. You'd ask, is the virus present in the tumor? And hit-and-run oncoviruses don't necessarily need to be. Does the virus transform cells in tissue culture? Not necessarily. Is the virus capable of causing tumors in animals? Again, that doesn't work either. So this is why people don't really use the Koch's postulates for oncogenic viruses in the first place, and why it wouldn't work for SARS-CoV-2. People have made an updated version of the Koch's postulates. This is sort of like using the gene approach. So basically saying a nucleic acid sequence should be present in most cases. And then essentially the more the copies you have, the worse the disease. Again, none of this is going to work for something that is essentially operating by chromosomal instability. So again, this is dated. This goes back to the 90s. And again, it relies very heavily on the oncogene hypothesis. There are other ways that people have established that certain cancers are oncogenic. So for example, Merkel cell carcinoma was established using the Zurhausen criteria. So Harald Zurhausen is a Nobel laureate, won actually the Nobel Prize for that. And this is how he did it. He said, okay, well, if we see persistence of viral DNA in tumor biopsies, we see growth promoting activities of those genes in model systems, and we can show that there's a continual viral oncogene expression that drives the cancer. And then if you can show that the virus infection represents a risk for the development of cancer. Again, notice that the way in which different viruses were established as being carcinogenic has varied from virus to virus. There's no one one-size-fits-all rule. For example, hepatitis C doesn't fit any of these because hepatitis C doesn't have an oncogene either. So the Zurhausen criteria would not work for that. So it's kind of been essentially an exercise in deductive reasoning that's been customized for each virus. That's why it's taken us so long to find these things, and that's why we keep finding them. The most recent one was, I think, 2007. So this is still going on. There's another set of criteria called the Hill criteria, and people have used this in the past as well. So, use temporality. The case must precede the outcome. You use a dose response. You use consistency, where you see it in different populations, specificity, and so on. If you now ask the question for, say, SARS-CoV-2, how would this work? Asymptomatic infections would make temporality impossible to assess, besides the fact that everyone's more or less gotten COVID, nearly everyone's gotten it at this point. The hit and run model makes the dose response irrelevant. Oncogenic viruses already have variably strong associations with cancer. An individual cancer may cause an individual virus may cause multiple cancers, and animal models don't even use the virus usually. They use a homologue. So again, the Hill criteria are a mess when it comes to establishing causality. So there are many reviews on SARS-CoV-2 and cancer, and most of them, to be honest, miss the point. The point is not so much that there are mechanisms that are supporting. The point is that in order to be able to show that SARS-CoV-2 is carcinogenic, if you use the hypothesis that the fact that it has double-strand breaks, unrepaired double-strand breaks and chromosomal instability, in order to be able to show that through epidemiological data is the work of a lifetime or two. So what does it really mean to prove something, right? So to show that SARS-CoV-2 is carcinogenic, you must demonstrate that it shows the same behavior as other viruses that have been demonstrated to be carcinogenic. We've already shown that. So the best that you can do with that is to show, okay, well, this is the hypothesis. Now, that hypothesis would then be leveled up to a theory over a period of time. So, for example, the continental drift hypothesis was proposed in the 1800s, became a theory in the 1960s. The hypothesis of evolution showed up in 1859, but it took 25 years. I'm pointing out here that you don't have to prove it to the level of a theory. If we have a working hypothesis that SARS-CoV-2 causes cancer on the basis of the fact that it causes the same changes as other viruses that are known to cause cancer, that's already quite a bit to say right there. And yes, we could wait a generation until it's proven to the level of a theory, but that's a whole generation that probably most of us don't have. So you can sort of prove it this way, right? With deductive reasoning. P implies Q. If P is Q, therefore Q must be true. So all men are mortal. Socrates is a man. Therefore, Socrates must be mortal. So you can modify this and say all sin-causing viruses are carcinogenic. To a first approximation, this appears to be true. I don't know of any sin-causing virus that's not carcinogenic. If anybody is aware, feel free to ping us on Twitter. If a virus causes sin, it is carcinogenic by implication. So virus X causes sin, therefore it is carcinogenic by that logic. Because the criteria for carcinogenicity at present overemphasize oncogenes, it's entirely possible that there are viruses that have not yet been proven to be carcinogenic that show this behavior. So again, as I said, to a first approximation, all sin-causing viruses are carcinogenic. If there are sin-causing viruses right now that are not carcinogenic, we should dig into them because, again, if you're not relying on the oncogene model, the question becomes how do you know those things are not actually carcinogenic? So this is the checklist for viral carcinogenicity that we were using previously. Does it cause persistent infections and does it infect dividing tissues? And then do you see the primary insults, which is DNA damage, unrepaired double-strand breaks, micronucleus formation, suppression of DNA repair? And then in addition, do you have any of the secondary insults? And as I said, SARS-CoV-2 cleans up on this particular checklist. So this is where we stand now. And you could say, look, let's do this from an argument from ignorance, right? So to claim that SARS-CoV-2 is not carcinogenic, right, we would have to use the argument from ignorance. We'd have to say, we need epidemiological data to prove that SARS-CoV-2 causes cancer. And if we don't see a change in cancer incidence rates, well, then we're fine. It's not carcinogenic, right? But this actually violates the precautionary principle, given the delays to oncogenesis. And given the repeated burden of infection, everybody getting this virus once a year, once every other year, once or twice a year. So the question at this point should be, given the asymmetric costs of inaction and given the irreversibility of those costs, what is the plausibility that SARS-CoV-2 is carcinogenic. In practical terms, this is what it means. As of today, we can unambiguously propose the hypothesis that it is carcinogenic. And let's say we have to wait 30 years, right? So let's run the numbers. So your baseline cancer risk is 0.02% per year. That's the actual number. 18 million new cases a year. We have 1 to 2 infections a year. Let's say one new infection a year. And you say that it's a 1.5 hazard ratio, right? What would this look like if you had a 5 or 30-year delay? So this is what it would look like with a 20-year delay and a 3.5 hazard ratio, for example. Here, what you can see is if the virus causes cancer at a 3.5 times increased risk, right? So you get SARS-CoV-2, you get a COVID infection, you're 3.5 times as likely. So it's a good sized effect. It's not, it's not small. And we're using a 20-year delay. What you notice is that by the time there are enough cases for people to start saying, wow, that's probably COVID, right? Let's say we set that panic threshold at 100%. You'd have 80 million cases of cancer that you wouldn't have had otherwise. And it would have taken you about 20 years, right? Now you say, okay, well, how many more cases of cancer are there locked in as a result of inaction during this period? And the answer is about 10 times that amount. So using these numbers, you can go to the website, which we have linked to in our threads on peer2pub.com, which Greg Kirchhoff hosts, and you can go run this yourself. But this little interactive tool lets you play with it. And the bottom line is, no matter what you do, the area in blue on the right is much larger than the area in red on the left. Because by the time you realize it's a problem, you've already baked in much more of that same problem in the future. And therefore, the logic being that if you insist on doing this in a way where you wait for enough epidemiological data, you're really dooming a lot of people to this. And what are we going to do if it turns out that, oh, it is carcinogenic and we now have an unambiguous epidemiological signal? It's not going to help you or me or anybody, not even the people who argued for inaction, because everyone will have gotten cancer 10 times, gotten COVID 10 times. So if COVID causes cancer, even the people who argue for inaction are going to find, FAFO, as they say, on that one. So that locked-in burden of disease is really important to consider from the standpoint of the precautionary principle. And the conversation right now that's happening around SARS-CoV-2 and cancer, in particular, the notion that without seeing epidemiological data, there's nothing to worry about, is wildly irresponsible. So summing up, the hypothesis that it's oncogenic is supported at this point by multiple aspects of its biology, as we discussed. There's multiple papers on this. Each of these points has multiple papers showing it. So at this point, where we are, it's fairly clear cut that this thing is plausibly carcinogenic. The existing frameworks of viral oncogenicity, many of which were devised on the fly for individual viruses, won't work for this one. So for this one, we're going to have to come up with a new framework, much in the same way as we did for hepatitis C, or much in the same way as was done for Merkel cell carcinoma. Every time something new comes along, you have to kind of, update your prior framework. SARS-CoV-2 is asymptomatic in a large number of the cases. Reinfections are widespread and expected on an annual basis. There's no DNA integration happening, no oncogenic signaling, and the transformation assay is not relevant anyway. The transformation assay asks the question, can you turn non-dividing cells into dividing cells? You don't have to even ask that question with SARS-CoV-2 because we already know it infects dividing tissues, for example, in the crypts of the intestine. So the idea that it has to turn quiescent cells into dividing cells doesn't even enter the picture. So given SARS-CoV-2's broad tissue tropism also, if it is carcinogenic, it will impact multiple tissues. So a lot of the criteria that we looked at are dated and don't account for these particular peculiarities of SARS-CoV-2, which means despite it very likely being carcinogenic, you're not going to be able to show it's carcinogenic using the criteria. So, and as we discussed, if we wait long enough, then we probably will see the signal, but by that time it'll be too late to do anything useful. So yeah, thanks for listening.
Thank you, Arijit. Very interesting. I just have a couple of questions that were inspired by your presentation. I guess one of the things I see is even with situations where the epidemiological signal ought to show up more quickly. So I'm thinking about secondary infections or, atypical rates or severities of different pathogens and so on. There's been a built-in dismissive explanation for those. So with those particular examples, immunity debt is the thing, right? So the
Yeah.
reason you're seeing more RSV, the reason you're seeing mycoplasma, the reason you're seeing all these other things is because we weren't infected. So there's this inbuilt system, and I think we're seeing that. I guess that my question is, do you think we're seeing that already with
Yes. So
carcinogenesis?
absolutely, yeah.
We
So
didn't do
in fact,
screening or whatever it is, right? Lockdowns.
yeah. So in fact, this is not really what it looks like. The baseline rate of cancer is not flat. This is actually what it's looked like.
Right.
Prior to COVID, this is what it looked like. And then there was indeed a dip right around COVID, and it did come back up. So in fact, there's been and I got it, yeah, hang on, I drew it wrong, but I'll redraw it. But just very roughly speaking, there was a slight dip in the early part of the pandemic. There was in fact a slight dip, right? And cancer rates are in fact rising, and in fact they were rising previously.
Mhm.
They were rising slightly, not 10 to 20 million. They didn't double, but you get the general point. So there was an increase. Cancer increase rates have been increasing for 20 years, and people don't fully know why. In the past 10 years or so, people have shown before the pandemic that the rates were going up. So this doesn't mean that rates going up with SARS-CoV-2 prove that it's not, that rates going up now prove SARS-CoV-2 is not carcinogenic. In fact, it's the opposite. It's even worse. If SARS-CoV-2 is carcinogenic, we're going to have to detect it on a rising baseline with noise and with that sort of screening dip. So the existence of competing explanations in this phase will only push out this detection point. And the further we push out the detection point, the worse the burden of disease will be. So the notion, every time we talk about this and people say, oh, but rates were rising before that. Yeah, think that doesn't call for inaction. That you should be more worried because rates were already rising. So, just because you were taking on water already doesn't mean there's nothing to worry about when you hit an iceberg. If you're in a boat and you hit a rock and your bilge compartment was half full already, you're going to sink faster, not slower. So the fact that cancer rates were already rising makes the whole thing more of a concern, not less of a concern. And the fact that people are arguing that means that we should wait till we see the signal clearly is only boils down to people arguing for greater levels of inaction.
I'll put a link in the description to our recent article on calm mongering. Um,
Right.
and there's, you alluded to merchants of doubt and very active, very well-funded efforts to undermine an appreciation for the carcinogenic role of tobacco. I wonder, I guess, with COVID, there is some of that for sure. But at the same time, I think there's just this propensity in public health to want to dismiss any of these scary possibilities. And so I even saw an article, I think this morning or yesterday, about breast cancer. They're detecting a lot more severe breast cancers, and the reason is there wasn't screening during lockdowns and so on. And I suspect some of that is
Oh, it is
very
probably
likely
true.
to be true, but there's never a mention in those articles like, and this widespread infection, could be a contributing factor. Likewise with other diseases, it's almost never mentioned. It's
And just to be absolutely clear, we're 4 years past the lockdown. And if the lockdown, if anything, in the US, for example, we were basically, some people didn't go to bars for 6 months. That was it. So even during the lockdown, I know people who went for primary checkups
Mhm.
during the lockdown. It's not like everybody stopped going. Quote unquote lockdown was 4 months long anyway, or 6 months long. So whatever burden there was, there's no way that 6 months of reduction of case detection by 50% could translate to 4 years of increased case detection by 20%. It doesn't, that's not how the
The
numbers
numbers
work.
were actually even more discrepant than that, I think, in the article that I was looking at.
Right. So
30%
yes, if
decrease
there
in
was a
infection, 60%, whatever. It was wildly.
right, if you had a dip over here,
Hmm.
So this is kind of like common sense, right? If this was your dip over here, then the area under the curve over here should be similar.
You would think.
You'd think, right? These two areas have to be the same. It can't be that you had the dip over here and then you had this. That's not deferred screening, just common sense. So when people make these arguments, the arguments are great for postponing action, but the arguments themselves have a time limit on them. They tend to age poorly. Many of these calm-mongering arguments tend to age poorly, of course, and then they're replaced by other calm-mongering arguments. But the point is that this one will also age poorly. But the damage is done, right? The damage is done. So the point is that the entire approach is wildly irresponsible. We're looking at risks where basically everybody's exposed to this once or twice a year at this point. And there's no substance that we expose ourselves to in sort of at that frequency without fully understanding what the health risks are. And if what we're saying is it may be carcinogenic, it's not the end of the world. I mean, sunlight is carcinogenic, and you know, beer is carcinogenic, and grilled meat is carcinogenic. So that's not the end of the world. But the point is, even in that case, you still have to work with the fact that there should be things that are being done in order to manage that risk. Right. So if it's carcinogenic and you say, look, it's carcinogenic, so take these steps to reduce your risk of a persistent infection. Now you're actually handling public health in a meaningful way. If you say, oh, how dare you say it's carcinogenic, you're fear mongering. That's the wildly irresponsible course of action, as we discussed in that calm-mongering article. That's the wildly irresponsible thing to do, and that is actually the thing that is harming health.
Do you maybe one more before we wrap up? But when we talk about carcinogens, you listed a bunch, and I think I don't remember the exact list of nine that you had on there, but a number of those were abiotic factors, right? So
Right.
cigarettes, alcohol, various other things, various chemicals. Do you think part of the issue is that we we would be better off in some ways if we used criteria or we used approaches? Yeah, so here you go. So radiate. So the first three of the first four, in any case, certain chemicals, are abiotic, right? And a bunch of the others
Yeah.
are intrinsic to the individual. Um, do you think part of the issue is that we treat uh, viral versus abiotic carcinogens very differently in our standards of evidence or our
Yeah.
mechanism of
Absolutely.
response, right? I mean,
Absolutely.
I
Absolutely.
I always, whenever these things are
Yeah.
discussed, I think about asbestos and the efforts
The
that,
the bar is set. Yeah, the bar is set bizarrely high for viral carcinogens in general, and to me, part of that is because that field hasn't updated its mental model, and what that field hasn't fully realized is that every time they show that something is carcinogenic, they have to kind of tweak their
right.
they have to tweak their framework a little bit, which means that they're using the wrong framework, right? So if you use the framework that we've discussed, right, you'll notice something very interesting. All seven viruses uh, work with this framework. If you use this as a generalized framework for demonstrating carcinogenesis, all seven viruses fit this. If you
Hmm.
try to use the Zurhausen criteria, or you try to use Koch's postulates, or you try to use some of the other ways in which people have shown carcinogenesis, you have to mix and match. You have to do special pleading every time. So the reason they're doing special pleading is because they're using the wrong paradigm, which is the oncogenic paradigm.
So if you
So
were to,
yeah,
yeah,
so
if you were to
any
use,
viral oncologists out there listening, like
yeah.
y'all should update your mental model.
Well, and what if you did this? So what if you adopted this the Chakravarty criterion instead and said we're going to go and do a scan of viruses that meet these criteria as potential carcinogens?
Yeah,
What do you think you'd
I
find?
have some ideas. I suspect CMV may be carcinogenic, for example. There's other viruses out there. CMV, I'm kind of like really uneasy about
Mm.
because again, everybody gets it. It's really hard to pinpoint. Um, and and yeah, it's one of those things where association studies will struggle. People have shown it to cause chromosomal instability, and it doesn't have an oncogene. So yeah, and
Yep.
again, it's not the end of the world if something is carcinogenic.
Hmm.
We routinely dabble in carcinogens every day, most of us, right? We're all exposed to carcinogens every single day. It's just that when you know something is a carcinogen, you behave rationally around it. So it's more about like behaving rationally. Denialism which has become sort of a cornerstone of our public health response, is just a really bad basis for living your life.
I think that's a really critical point that you've raised. That there's not any intent here or value really in panicking about it being carcinogenic any more than alcohol or diet pop or whatever it is that people indicate some risk. It's recognizing that and being able to factor that into your decision making and where you can mitigate that in a fairly straightforward way. So, for example, if removing asbestos will mitigate that, or smoking bans will mitigate that, then we can have that
Yeah,
conversation about that in terms of public health.
yeah,
Nobody's talking about banning alcohol again, right? As a
yeah,
result of
exactly.
carcinogenic. It's about
Yeah,
informing.
exactly. It's about informed decision making. And so the notion of the risk cannot be discussable because somehow the mere discussion of risk will panic everyone, is just Orwellian, right? Because actually, it's much scarier to realize that there are risks circulating that no one's doing anything about than if, in fact, if we were having rational discussions about these things in the public sphere, I think that would be much more productive and frankly speaking, um, much more likely to lead to constructive outcomes.
Mhm. Especially when you can have combined efforts. So if there's a number of viruses that do meet these criteria, and they can all be mitigated with similar strategies, clean the air, for example.
Yeah,
It just
exactly.
adds to the,
I
the,
mean,
the appropriate calculus on whether that's worth doing.
if you just clean the air already, like you'd get rid of a lot of these issues.
Hmm.
Um, but whether or not you clean the air, the point is we have the right to know whether something is or isn't carcinogenic. The notion that we shouldn't ask the question because somehow it may be disturbing or you know create panic, um, is something that gets pushed. That don't panic just yet. We don't have any data. By the time everybody finds out that in fact it is carcinogenic because you can't hide the signal, if it is carcinogenic, um, it'll be too late to do anything about it. So if we were to use a formal criterion that said, look, this is what it looks like. To me, like, is it a slam dunk? Is it done? Should we immediately classify it as a carcinogen? In my opinion, no. In my opinion, there's still one more smoking gun experiment that needs to be done. Show that long COVID patients who have persistent viral infections in the gut, in the intestinal tract, have a higher rate of cancer. If you can show that, for example, um, in a very focused way, then now you have an association. So that is one experiment that could be done tomorrow. A supporting experiment for that one is take cells that are actively dividing from intestinal crypts and show that they are harboring the virus or that they are harboring DNA damage. So if you had crypt biopsies and you were able to show unrepaired DNA double-strand breaks and micronuclei, even before getting to the epidemiological data, you could show with deductive reasoning by demonstrating the presence of DNA double-strand breaks and micronuclei in crypt biopsies, that this thing is damn likely to be carcinogenic. Once you've shown that for one tissue, however many other tissues show up later on, or however many other kinds of cancer show up later on, that's additional. That'll inform your risk, but you've already classified it as a carcinogen, in my opinion, at that point.
Yeah, one of the things that's concerning, or I think worth being aware of in that case, is when we've talked about things like the evolution of persistence versus acute severity.
100%. Exactly.
It's a tropism to tissues like that, right? Like that's
It's a
where it's going
tropism
to
to
go.
tissues like that. So exactly. So any public health strategy that's based on letting this virus spread continuously, we should have a conversation about what does it mean if we start racking up the persistent infections and what are the likely consequences of persistent infections,
Yeah.
even beyond this, because that graph I showed you about the delayed effects, that's true for 20 other potential things. So when we read papers that say, oh, this thing causes, increased risk of heart attacks for up to 3 years, that up to, as somebody pointed out on Twitter, it's not up to, it's for at least.
So
And so
far,
the true
right?
burden, yeah, it's at least. And so the true health burden of an emergent disease with delayed consequences is never visible during the phase of emergence. We are still in that emergent phase. We haven't finished tallying up the bill. It's like going to the grocery store, standing in the checkout line. You've checked out half your stuff and it's only $80. But most of your groceries are still on the belt. So don't be excited about the fact that this week's groceries were only $80. The bill hasn't come due yet.
Yeah, no, I agree. Very interesting,
All
and
right.
I think that's a really important point that this is not about, panicking. It's about rational discussion, about standards of evidence, and about practical decision making and public health that's informed by these real possibilities. And I think that's very useful. And I think there's broader implications too for our understanding of how cancer generally works, which is really
Yeah,
important.
I think there's some very fun, interesting basic science questions here as well. But I'm not a basic scientist, so I'll leave that to you guys. Great.
Very cool. Excellent. Thanks so much. And we will have this posted soon. And don't forget to check out some of the links in the discussion forum or in the description below. We'll have links to some Twitter threads, our article on column mongering, and a few other things like that. And don't forget to check out episodes 1 through 3 if you haven't seen them yet. Talk to you soon.
Great. Bye.